Hello, I'm Naga Irkulapati, doing my PhD at Chalmers University of Technology. I presented this work during the recent European Conference on Optical Communications, which is called as ECOC 2013 on 25th of September in London. I would like to present this work again in this video. The title of the talk is Extending Digital Backpropagation to Account for Noise, and I would like to acknowledge my co-authors Henk Wijmeers, Pontus Johannisson and Erik Egrell, and would also like to thank other colleagues at Fiber Optic Communication Research Center Force at Chalmers for stimulating discussions during this work. In this work, we propose a map-based detector that takes the noise from the amplifiers into account, and by doing so, our aim is to account for the signal-noise interactions and get closer to the fundamental performance limits. Through simulations, we show that the system reach is increased by over 20% of the conventional digital backpropagation for the system that we have considered. This will be the outline of the talk. First, I will introduce you with the problem formulation, and then we'll tell you about our approach, which is based on MAP criterion. To better understand the underlying concepts of the approach, I will walk you through two examples, first for the systems without memory and then the systems with memory. Then I will show you simulation results for dispersion managed links and also uncompensated links. So the system consists of a transmitter, dual polarization transmitter followed by a modulator, and it consists of an N-span fiber optical link with each span consisting of a single mode fiber, an optional dispersion compensating module for the case of dispersion managed links, and followed by an EDFA for compensating for the losses in the fiber. As we all know, the received signal in this type of systems is impaired by additive noise from the amplifiers and also the dispersion and nonlinear rotations within the fiber. Through DSP, these impairments can be handled either by compensating only for dispersion through electronic dispersion compensation and techniques which take care of nonlinearities also, like Volterra series based and the famous technique called digital backpropagation. In this plot, we see the simple error rate as a function of input power for electronic dispersion compensation, which is in blue, and for digital backpropagation, which is a green curve. Here we can see that digital backpropagation has a much improved performance compared to electronic dispersion compensation. It is often argued that digital backpropagation is the ultimate technique for compensating linear and nonlinear impairments in the setup that we are considering now. However, it doesn't take the noise from the amplifiers into account. So we wanted to know if by taking the noise from the amplifiers into account, can we develop algorithms which are better than digital backpropagation? Of course, the answer is yes, otherwise I would not be talking to you now. Because of the similarities we have with digital backpropagation, and since we take the statistics of the signal into account, we name the proposed algorithm as stochastic digital backpropagation. So coming to the problem formulation, given the received signal Rn of t, our aim is to estimate the transmit data, as simple as that. And to solve this, we use a maximum a posteriori criterion, which computes the mode of the posterior distribution of transmitted data given the received signal. And to solve this problem, we will use factor graph and sum product algorithm. Due to time constraints, I will not cover these in detail. Interested readers can go through the references in our paper or go through the reference here. However, I would like to give you a high-level overview of the approach here. Here you can see the same system model that we have seen before. Consider some intermediate variables x, y, z and the received signal Rn. So given this received signal, what DBP does is it tries to estimate the signal at each of the forward blocks. So you can see here that it tries to estimate the signal z hat, y hat and x hat corresponding to the signal in the forward system. What stochastic digital backpropagation does is it tries to find the distribution of the variable at each step and propagate this distribution through each of the blocks. So here we start with Rn, we try to find out the distribution of z given Rn, and then we backpropagate this distribution and we take the decision based on the distribution that we have here. I would like to point out that since we don't have closed form expression of the distribution for this system model, we represent the distribution with a list of particles or samples and propagate these samples at each stage. So let us see some simple examples for better understanding this concept. Consider a simple scenario where we have two spans, and consider an ideal scenario where the dispersion is completely compensated by dispersion compensating module and we are only left with nonlinearities and noise from amplifiers. So x1 is just affected by the nonlinear effect. Similarly, R2 and x2 are just affected by the additive Gaussian noise. X1 and R1 are also affected by additive Gaussian noise. R1 and X2 are also affected by just nonlinear effect. So here, given the received signal, here we can see a scatter plot of 16 count constellation. Suppose we have received the signal R2. As we said earlier, X2 and R2 are related by additive Gaussian noise, with x2 having a mean of R2 and variance equal to variance of the noise. So we represent this distribution for x2 with particle representation as discussed earlier. So here you see the particle representation for the distribution of x2. Now the message for R1 is found by rotating the particles, where rotation per particle is proportional to the power. Then we compute the message for x1 by adding the noise, and finally we get the message for A by rotating the particles. Given this message A, we have to compute the posterior distribution. One way to do this is by approximating the cloud of samples with a bivariate Gaussian distribution and evaluate this distribution at each of the constellation points. This will lead to the final decision for the maximum posterior rule. Now let us see a more practical case with a system with dispersion. The main difference between this and the previous slide is that all the variables here will be vectors, as we have to take into account for dispersion. Also, let us consider only one span of SMF, fiber Bragg grating as a dispersion compensating module, and an EDFA. Here we can see the waveforms at the intermediate stages of the forward system, and here is the received signal R. Now to represent the uncertainty in the variable, we use the particle representation as I said earlier. Since we have a waveform here, the uncertainty in this variable here, which is a waveform, is captured by particle representation, which is a collection of waveforms here in gray color. So these particle waveforms are passed to the inverse of each blocks of the forward system as seen here, and we pass these particle waveforms through a filter matched to the pulse shape followed by a symbol rate sampler. Then we end up the same case as earlier, that we have for each symbol we have corresponding number of particles, and we then approximate these particles with a bivariate Gaussian distribution and evaluate this distribution at each of the constellation points, which leads to a symbol based decision. We note that when the noise is absent in the amplifiers, these gray waveforms converge to the blue one, which is the mean waveform, and the stochastic digital backpropagation reverts back to the conventional digital backpropagation. Now let us see some simulation results. In the transmitter, we have used 16-com or QPSK as modulation formats. We have used a root raised cosine pulse with a roll-off factor of 0.25, and we have simulated the system with different baud rates. As you can see here, this is the SMF is of length 80 kilometers with dispersion and nonlinear parameter and losses as given here. The dispersion compensating module can be either a dispersion compensating fiber or fiber grating, and as I said earlier, we have used this DCM for dispersion managed links. And the spontaneous noise emission factor for EDFA can be seen here. The receive signal is sent through digital backpropagation and also through stochastic digital backpropagation. I would like to point out that we have used an ideal step size, that is, whatever step size we have used for the forward system, we have used the same step size for the backward system. That is, we have many segments per span, and since we wanted to find the fundamental performance limits, we didn't care about the complexity of the system. So we have used, for example, step size of this, which is from this paper here. So here you see the simple error rate for dispersion managed system with fiber grating as a dispersion compensating module with respect to the input power. Here this is simulation is for a 14 gigabaud. Here blue curve represents digital backpropagation and black is for stochastic digital backpropagation. One thing that you can immediately see is that there is a difference in optimal powers for these two algorithms. The simple error rate has improved a lot, and also the curves have shifted to the right, which means that this stochastic digital backpropagation is more tolerant to the nonlinear effects. It has around 2 dB gain here. We have done the same simulation for different baud rates for the same system as previous, but for 28 gigabaud. Here also you can see the same conclusions as before, that the optimal power has changed, simple error rate has improved, and there is a gain in terms of nonlinear threshold. This plot shows the simple error rate versus input power for uncompensated link, meaning we didn't use any inline dispersion compensating module. We see that the gains for stochastic digital backpropagation are not as much as we saw for dispersion managed links in the previous slides. Our explanation for this behavior is that for uncompensated links, the strength of the dispersive effects is stronger than for dispersion managed links. So as the strength of this dispersive effects increases, the nonlinear effects and hence the signal noise interactions become weaker, so we get lesser gains. As a result, we can see that DBP, which doesn't take noise into account, is still close to the stochastic digital backpropagation. Here you see the simple error rate versus the system reach or the transmission distance, and here we can see the digital backpropagation and stochastic digital backpropagation plots. Here you can see that the system reach has been increased by around 18% for this 28 gigabaud system that we have. This is for dispersion managed link with FPG, fiber grating. And here we can see the same system as in previous slide, but for different baud rates. And one thing that we can notice is that as the baud rate is increasing, the gains are decreasing. We observe this behavior for uncompensated links also, and also when we have QPSK modulation format and dispersion compensating fiber as dispersion managed link in a dispersion managed link. The reason is, as explained earlier, is maybe because of the increasing strength of the dispersive effects as the baud rate is increasing. So to conclude the talk, we have proposed an algorithm which is based on maximum a posteriori formulation, and that takes the nonlinear signal noise interactions into account. Using this approach, we aim to get closer to the fundamental performance limit, and through simulations we have shown that the system reach can be increased by over 20% for dispersion managed links. Thank you for listening. If you have any questions, please email me at vnaga@shalmas.sc. Thank you.